Light. It's what draws us to the night sky and what ruins half our shots. Those same photons that reveal galaxies can also drown your images in glow, noise, and pollution. So, how do we fight back? Welcome to Edisla's ultimate guide to astrophotography filters. In this video, we'll dive deep into filters, what they do, how they work, and how the same filter can behave completely differently on different optics and cameras. You'll also hear real learnings from fellow astrophotographers and the lessons they picked up along their journey. By the end, you'll know exactly how to choose, use, and master filters, covering brands, use cases, and budgets to truly tame the night sky. And for beginners, we've got a very special section at the end, packed with advice that will completely redefine your astrophotography thinking. Don't miss it. Before we jump into filter types, brands, or budgets, there's one fundamental thing we need to understand. What light are we actually trying to capture, and what light do we want to block? Don't worry, we won't get lost in physics. We just need a clear idea of the sources of light in the night sky and how they behave, because that understanding forms the foundation of every filtering decision you'll make. Let's start with the light we want. In astrophotography, we call it the signal. When we look up at the sky, stars are the most obvious targets. Our sun is the perfect example, a hot, dense ball of plasma that emits light across the entire visible spectrum, from deep reds through yellows and blues. Stars like it and the countless stars in the Milky Way radiate broad-spectrum light because they are essentially natural cosmic furnaces. Their atoms collide and vibrate constantly, producing a smooth continuum of colors rather than just a few isolated lines. A telescope pointed at the Pleiades cluster or the Orion belt collects all this broadband starlight. And when we move further out to galaxies like Andromeda, the story is the same on a grand scale. Billions of stars plus dust clouds and star-forming regions all blending their light together into a broad, continuous spectrum. That's why, when we photograph galaxies, we want to preserve as much of this natural light as possible, while still cutting out the glare of earthly interference. Now, nebulae are a completely different story. Take the iconic Orion Nebula, for example. Unlike stars, nebulae are vast, cold, diffuse clouds of gas and dust. They don't glow across the entire spectrum. Instead, they shine only in very specific wavelengths. Their atoms only emit light when excited by nearby stars or shock waves, and each type of atom has its own signature wavelength. Hydrogen glows in deep red H-alpha, oxygen in TL03, and sulfur in another red S2 line. These are sharp, precise emission lines, not a broad rainbow. That's why nebulae are the perfect targets for narrowband filters, which isolate these exact colors while blocking everything else. Nebulae themselves come in several types, and each behaves slightly differently. Emission nebulae, like the Lagoon Nebula or the Heart Nebula, glow because their gas is energized by nearby young stars, producing strong emission lines ideal for narrowband imaging. Reflection nebulae, like the famous Pleiades dust clouds, don't emit light at all. They scatter the light of nearby stars, which is why they often appear bluish. Because they reflect starlight, broadband filters are better suited here. Then there are dark nebulae, like the Horsehead Nebula, which are dense clouds of dust blocking the light behind them, forming dramatic silhouettes against brighter backgrounds. Finally, we have planetary nebulae, the colorful shells of gas expelled by dying stars such as the Ring Nebula, and supernova remnants like the Veil Nebula, both of which shine strongly in specific emission lines and respond beautifully to narrowband filters. Planets offer yet another type of light. They don't generate their own visible light, they simply reflect the sun. Mars shines strongly in red and near infrared, Jupiter and Saturn reveal sharper cloud details in infrared, and Venus glows in ultraviolet, highlighting its thick cloud cover. Each planetary target benefits from filters that enhance the wavelengths that bring out their best features. So here's the key takeaway. The type of light a celestial object produces completely shapes how we capture it. Once we know what to protect, the signal, we can turn our attention to what needs to be reduced. The noise. Light pollution from streetlights, billboards, and the general glow of cities scatters upward and washes out the faint cosmic light we want to capture. This unwanted brightness becomes the noise that works against our images. The simplest way to reduce it is to move away from light-polluted areas, and we measure how dark or bright a sky is using the Bortle scale. On this scale, Bortle 1 represents the darkest skies, while Bortle 9 is the most polluted. Most astrophotographers live under Bortle 5 to 8 skies, where light pollution is almost impossible to avoid. Traveling to darker locations helps, but filters are what make regular, everyday imaging achievable. In moderately dark Bortle 3 or 4 skies, mild broadband or light pollution filters are enough to reduce the glow from sodium and mercury lights without drastically altering color. In brighter Bortle 5 and 6 skies, dual band or UHC filters become more effective, isolating the key nebula emissions, H-alpha and O3, while suppressing much of the urban glow. Under the severe brightness of Bortle 7 to 9 skies, ultra-narrowband filters are essential. They allow you to capture nebulae such as Orion, Lagoon, Horsehead, or the Veil, even when they're completely invisible to the naked eye. Filters will never fully replace the quality of a truly dark sky, but understanding your Bortle level and selecting the right filter gives you the best chance to recover as much of the night as possible. Now that we've covered the basics of signal and noise, we can move on to the next important part of the process, the camera. Astrophotography is built upon 2 main sensor families, OSC and mono. An OSC one-shot color camera works much like a digital version of the human eye. Every pixel is already covered with a tiny red, green, or blue filter, the Bayer matrix, so it captures color by design. Any filter we attach must work with that mosaic, not against it. An OSC can't separate wavelengths that its sensor isn't built to interpret, which is why OSC imagers rely on broadband tools, dual band filters, and modern multiband options that divide H-alpha, O3, and S2 into signals the camera can decode. These filters act as translators specifically tailored for color sensors. A monochrome camera, however, is something entirely different. A monosensor sees every photon directly, no built-in color filters, no bias, no restrictions. Color comes later during processing. You choose the wavelengths. You build the palette. And with that freedom comes access to the full range of astrophotography filters. True H-alpha, O3, S2, LRGB, near-infrared, ultraviolet, and more. Mono setups isolate wavelengths with exceptional precision, cut through light pollution, and reveal detail that an OSC simply can't reach. This is why mono remains the gold standard when time, budget, and ambition are aligned. Even after we separate cameras into OSC and monochrome, there's one more factor that can dramatically influence how filters behave: pixel size. Professor Vijay Sudhir demonstrated this with a controlled experiment. He photographed the same emission nebula using the Asker SQA-55 telescope and the IDS NBZ dual band filter. The only variable: the cameras. One was a 183 MC Pro with tiny 2.4 micron pixels, the other a 2600 MC Pro with larger 3.75 micron pixels. Everything else, sky, exposure, processing, remained identical. The difference was striking. On the ASI 183, colors stayed clean and distinct, red remained red, green remained green, and almost no yellow appeared. On the ASI 2600, yellow patches emerged in regions where the nebula should emit only red, and green as emission nebulae don't emit yellow. Then why there's yellow? The reason is pixel geometry. Larger pixels can allow red and green photons to land on the same pixel, blending them into yellow. Smaller pixels capture each wavelength separately, keeping colors true. Interestingly, at longer focal lengths, the larger pixels perform better. The incoming light cone spreads, separating wavelengths before hitting the sensor. The takeaway? Even the most carefully chosen filter will behave differently depending on the sensor it sits in front of. In other words, the perfect filter doesn't exist in isolation. Its behavior is shaped by the light from your target, the filter's properties, the optics of your telescope, and the geometry of your camera sensor. With that understanding, we can now move on to the heart of the guide, the types of filters themselves. Let's start with the gentlest of them all, the broadband filters. These are the closest thing to natural eyesight in astrophotography. When you use one, it doesn't try to reinvent the sky, it simply polishes it. A broadband filter opens its arms to a wide stretch of the spectrum, reds, greens, blues, and only trims the orange haze from old sodium lamps or the faint glow of mercury vapor lights. Stars stay true to their colors. Galaxies preserve their delicate gradients. Reflection nebulae continue to shimmer in that faint, honest blue cast. In places where the sky is not yet drowned by LEDs, Bortle 3, 4, maybe even 5, broadband filters feel like slipping on glasses that bring the night into clearer focus. But under the crushing brightness of a modern city, in the Bortle 8 and 9 zones where LED light fills every wavelength, The broadband filter can only whisper. It simply can't overpower pollution that spans the entire spectrum. Still, for natural color targets, under even moderately cooperative skies, broadband filters remain irreplaceable. Then, as we take a step deeper, we arrive at the filters that reshaped astrophotography forever, narrowband filters. Where broadband filters are gentle, narrowband filters are surgical. They don't let in a rainbow, they let in razor-thin slices of the spectrum, the exact slices where nebulae shine. Hydrogen's deep red at 656 nanometers. Oxygen's cool teal at 500. Sulfur's crimson at 672. These aren't arbitrary choices, these are the fingerprints of the cosmos. Emission nebulae glow in specific atomic lines, and when a filter isolates one of those lines, everything else, light pollution, moonlight, city glow, falls away into darkness. Even under a Bortle 9 sky, the nebula still speaks. Some narrowband filters isolate just one of these lines, perfect for monochrome cameras that thrive on precision. Others combine two, such as H-alpha and O3, so that one-shot color cameras can gather rich nebula detail even from balconies and rooftops. And then there are the ultra-narrow filters, the 3 nanometers, 4 nanometers, sometimes even tighter designs, crafted to silence nearly all unwanted light. These are the tools of astrophotographers who battle the deepest urban sky glow and still emerge with breathtaking detail. From there, we slide naturally into the evolution of the narrowband world, multiband filters. These are the modern reinforcements for OSC imagers. Instead of choosing between 1 or 2 narrow windows, these filters open 3 or 4. H-alpha, O3, S2, all carved into a single piece of glass. In one exposure, a color camera can gather the chemical signatures of an entire nebula. No filter wheel, no changing filters in the cold, no waiting for another night of clear sky. Just one filter working in harmony with the Bayer matrix to deliver structure, color, and contrast. They don't quite reach the purity of mono with dedicated filters, but they come remarkably close. And for anyone imaging from heavily polluted skies, they feel like a revelation. Take our user, Senorita Datta, a photographer working under the Bortle 9 skies of Calcutta. With a solid background in traditional photography, he gradually expanded into astrophotography and learned to use advanced filters with his OSC camera. For his Rosette Nebula project, he combined the Antlia 3 nanometers ALPT to capture S2 and O3, the Optilong L Ultimate for H-alpha and O3, and the Antlia Tri-Band RGB Ultra 2 to pull out clean RGB stars. By separating each signal and blending them in post-processing, he created a final image that stands shoulder to shoulder with results from dedicated monochrome setups. This workflow closely reflects the techniques used in true narrowband imaging, making it an excellent stepping stone for anyone preparing to move into monosystems later. It's a perfect example of how modern multiband OSC imaging continues to evolve and open new possibilities for astrophotographers. But if you want to speak the language of true color with absolute control, then you eventually arrive at the classic palette LRGB. This is the method that has shaped professional astrophotography for decades. A monochrome camera paired with luminance, red, green, and blue filters allows you to collect detail and color separately, then weave them together like layers of paint. The luminance channel captures the fine detail, the texture of galaxies, the structure of clusters, the sharpness of nebula edges, while the RGB filters provide the hue. Under dark skies, there is nothing more powerful. Under heavy city glow, though, LRGB struggles for the same reason broadband does. The sky pollution is simply too broad to fight back. And then we turn our attention to a completely different class of targets, planets. Planets don't glow, they reflect. Their secrets hide not in emission lines, but in subtle shifts in reflected sunlight. Planetary filters aren't here to suppress light pollution. They exist to reveal detail. Infrared pass filters cut through atmospheric turbulence to uncover the structure hiding on Jupiter or the subtle textures on Mars. UV filters reveal the high-altitude patterns swirling over Venus. Methane band filters isolate the reflective signature of cloud tops on Jupiter and Saturn, revealing storms and layers invisible in normal light. And then there is the sun, the one object we must address with absolute seriousness. Solar filters aren't creative tools, they are shields. They block 99.999% of sunlight, turning a dangerous blaze into something safe to observe. White light filters reveal sunspots and granulation. H-alpha solar filters expose prominences and filaments that dance across the chromosphere. CAK filters show the high-energy regions deeper in the solar atmosphere. Solar imaging is thrilling, but it demands respect. The sun is not a negotiation. So in the end, the way we choose our filters comes down to just two things: the kind of light our target produces and the kind of light our sky tries to drown it with. This is the logic behind every filter you'll ever hold. Now that we've covered the basics and types of filters, let's take a quick look at some key specifications you'll encounter before moving on. Transmission curve. This is essentially the window your filter opens in the spectrum, showing where a light passes through, and just as importantly, where it doesn't. High-quality filters have walls like cliffs, sharp, steep, unyielding. Cheaper filters have walls more like hills, sloped, soft, and imprecise. In astrophotography, even the smallest leak of unwanted light can wash out the contrast you've spent hours capturing or bury a faint nebula entirely. Bandwidth numbers, like 7 nanometers or 3 nanometers, are more than labels. They define the width of your filter's window. Narrower windows cut closer to the heart of an emission line. A 12 nanometers H-alpha filter captures the glow surrounding a nebula. A 7 nanometers filter sees the gas itself, and a 3 nanometers filter isolates individual atoms. Narrower windows sharpen the universe, the sky darkens, the background disappears, and faint details pop. Under a light-polluted Bortle 9 sky, a 3 nanometers filter can perform like a 7 nanometers filter under Bortle 3 conditions. But precision comes at a cost. Narrower windows demand exact encodings, making the filter more of a scientific instrument than a simple piece of colored glass. Coatings. These are the silent architects of your night sky. High-end filters use multiple layers of dielectric coatings with microscopic precision. Each layer is engineered to reflect or transmit specific wavelengths, shaping the transmission curve with mathematical accuracy. Cheaper coatings drift, warp, scatter, or shift with temperature, humidity, or steep light angles. When coatings misbehave, the results are immediate: bright halos around stars, unwanted reflections, distorted colors, and blurred fine details. Halos, the heartbreakers of astrophotography. These ghostly rings around bright stars are caused by internal reflections inside the filter, bouncing between coating layers. Cheap filters almost always produce halos. Mid-range filters sometimes do, premium filters almost never do. You notice the difference instantly when imaging objects like the Horsehead Nebula or the Pleiades. Fast optics, systems like RASAs, hyperstars, 2 astrographs, and fast refractors introduce another challenge. Light hitting a filter at steep angles can shift the filter's effective wavelength. A 3 nanometers H-alpha filter designed for an f7 scope may no longer align with the true H-alpha line at f2. The nebula fades, colors shift, and emission lines like OIII or S2 become unusable. That's why manufacturers offer fast system filters, specifically engineered for steep light cones. Parfocal filters. Another practical consideration is parfocality, especially for multi-filter imaging setups. A parfocal filter is designed so that when you switch between filters, your focus remains nearly the same, requiring minimal adjustment. This is a huge time saver during imaging sessions, especially for narrowband mosaics or when using filter wheels. Non-parfocal filters force you to refocus every time, which can slow down your workflow and introduce tiny misalignments across frames. Premium filters tend to maintain parfocality across the set, while cheaper filters often vary, meaning more refocusing and potential frustration. Filter size. The physical size of a filter isn't just about fitting your telescope, it's about matching your optical system and camera sensor for optimal performance. Filters come in a variety of standard sizes like 1.25 and 2-inch mounted, or unmounted 36 and 50 mm, and even larger square or rectangular formats. Choosing the wrong size can lead to vignetting, uneven illumination, or physical interference with your optical train. When selecting a filter, consider your sensor size. Larger sensors, like full-frame or APS-C cameras, require larger filters or square filters to fully illuminate the field without causing dark corners. Small 1.25 inches round filters may work for small sensors or eyepieces, but will severely vignette a full-frame camera, especially at fast focal ratios. Conversely, using an oversized filter on a small sensor is generally fine, though it may be more expensive and add unnecessary weight. The optical design of your telescope also matters. Fast, wide-field systems like RASAs require larger filters to avoid edge cutoff, while slower, narrow-field scopes may work well with smaller sizes. For filter wheels, round filters must match the wheel slots, and square filters must fit the trays or holders precisely. Anything misaligned can cause light leaks or reflections. Once you understand these factors, filter charts stop being mysterious graphs and start becoming roadmaps for your imaging. Quality matters far more than the number on the box, and the next chapter will explore brands. Why some filters are expensive, some are budget-friendly, and how they perform across different price points. We begin where precision is absolute, the ultra-premium tier. This is the realm of filters built like scientific instruments, crafted for research labs and observatories. At the top sits Astrodon, a name spoken with almost mythical respect. Astrodon filters are celebrated for their flawless consistency, incredibly steep cutoffs, and near zero halos, even with the brightest stars in the sky. They don't shift, they don't drift, and they don't surprise you. They simply work every single time. We're not sure if they're formally in the business, but our team at Edisla has used their products firsthand, and we love them. Their gear is truly legendary. Standing right beside them is Chroma. Chroma supplies filters for aerospace imaging, scientific detectors, and professional telescopes. Their coatings are engineered with microscopic precision and superb out-of-band blocking that remains stable across temperature changes and fast optical systems. With Chroma, what you see on the spec sheet is exactly what you get on Sky. Ultra-premium filters are expensive, but they're expensive for one reason: they're perfect. They're the filters you buy once and trust for a lifetime. From here, we move into a tier that's become the sweet spot for serious imagers, the premium affordable category. These brands deliver nearly premium performance, but without the painful premium price. Leading the charge is Antlia. In just a few years, Antlia went from underdog to industry disruptor. Their Pro Series and ALPT dual bands offer fantastic blocking, minimal halos, and exceptionally narrow band passes, often rivaling filters that cost twice as much. Next is Astronomic, the German manufacturer known for their rock-solid optical stability. Their Max FR series is engineered specifically for fast systems, and their coatings stay consistent even after years of temperature swings and heavy use. Astronomic has earned a reputation for longevity and reliability. Bader follows as one of the longest-standing innovators in amateur astrophotography. Their CMOS-optimized filters, their fast system variants, and their well-refined multi-band light pollution filters all reflect decades of development. Bader's strength is balance, excellent performance without excessive cost. Bader Solar Film is like the Google of solar filters. And then we have Pegasus Astro, a rising name delivering modern filters with impressive halo control and tight quality standards. A newcomer, yes, but one that's quickly proving it belongs in the premium arena. This tier is where ambitious astrophotographers thrive, those who want professional-level performance without paying ultra-premium prices. As we travel farther down, we enter the world that most imagers are familiar with, the normal tier brands. This is where affordability meets practicality. These filters may not reach ultra-premium precision, but they're widely used, widely trusted, and capable of producing stunning results. Optilong leads this category as the go-to option for beginner and intermediate imagers, famous for redefining one-shot color astrophotography. Filters like the L-Enhance and the L-Extreme, yes, the ones you see everywhere, made it possible for OSC users to capture shockingly detailed nebulae from light-polluted skies. Right behind them are brands like ASCAR and ZWO, companies building filters that complement their own cameras and telescopes, completing their ecosystems rather than competing with the premium giants. And then there's OIII, a Japanese brand built on scientific optical engineering. OIII's filters don't just block light pollution, they sculpt the spectrum to maintain color balance, giving natural results that many imagers swear by. Finally, Hutech, a quiet but respected manufacturer known especially among DSLR and astro-modified camera users. Their filters are clean, stable, and often chosen by advanced shooters who value precision over marketing hype. This tier is the backbone of the hobby, affordable, accessible, and capable of truly beautiful results. And at the entry point of the market, we reach the budget tier, the gateway for newcomers. Here you find SV Boni, the most recognizable brand in this category. Their filters are simple, accessible, and perfect for learning the basics without a major investment. And alongside them, you'll find a growing family of OEM manufacturers, new brands producing budget-friendly filters that make astrophotography possible for more people than ever before. Choosing the right filter starts with knowing your gear: camera, sensor, telescope, optical speed, sky conditions, and budget. Once those are clear, the path is straightforward. Now let's see how to choose a filter based on your skill level. At the very beginning, as a beginner, your goal is simple: learn the sky, learn your camera, and learn your workflow without spending a fortune. If you're using an OSC camera, start with a single dual band or tri-band filter from brands like Optilong, Ascar, ZWO, or Edisla. These filters simplify the process and deliver dramatic results right away. If you're using a mono camera, start with H-alpha and luminance. Just these two bands will teach you more about astrophotography than any tutorial ever could. At this stage, you don't need perfection. You need experience, the kind that comes from capturing, processing, and learning under real skies. Once you've gained confidence and experience, you move into the intermediate stage, the stage of expansion. By now, you know your sky, your telescope, and how your camera reacts. You're ready to build a real filter set. For OSC users, this means upgrading to a premium multi-band filter, such as the Antlia ALPT or IDS NBZ, or even moving into mono imaging. Mono users expand their palette with H-alpha, O3, S2, and add LRGB for galaxies. At this level, you start noticing subtle issues: halos around bright stars, small shifts in bandpass with fast optics, and the value of high-quality coatings. Stretching into the premium, affordable tier with brands like Antlia, Beta, or Astronomic pays off immediately. The difference is visible in your images, and it becomes part of your learning curve. The next phase is advanced, the stage of precision. By this point, experimentation has given way to optimization. You know which stars tend to ruin your frames, you understand exactly how fast your optics are, and you've learned just how much your sky can fight back. Filter choice becomes deliberate, intentional. You start selecting narrow band passes like 3 nanometers, 4 nanometers, paying close attention to halo resistance, angle shift, and overall transmission. Choosing filters becomes like a painter choosing brushes, every decision purposeful, every detail considered. Most astrophotographers spend the majority of their time here, honing their skills, exploring new combinations, and pushing their equipment to its limits. Premium, affordable filters serve as the reliable baseline, while ultra-premium remains the aspiration, the ultimate goal for those chasing perfection. This is where creativity meets technical mastery, and where the images you capture begin to truly reflect your vision under the stars. Finally, there is the professional stage, the stage of zero compromise. At this level, your filters are no longer accessories. They are scientific instruments. Astrodon and Chroma are the only options that meet these standards. Not for the prestige of the name, but because your imaging demands absolute consistency. Perfect cutoffs, stable coatings across f2 to f10, zero halos, maximum transmission. Professionals don't buy filters, they invest in them. At this stage, the filter doesn't just contribute to your system, it defines it. Even after we've covered coatings, bandwidths, transmission curves, and sensor types, there's something every beginner needs to hear. Because this hobby can get overwhelming quickly. When you first step into astrophotography, you see breathtaking images, premium filters, and top-notch optics. It's easy to think, if I buy that gear, my photos will look like that. But the truth is simpler and much kinder. Success doesn't come from owning every filter. It comes from mastering one filter deeply. Here are some tips for beginners from Edisla. Most beginners start by buying a budget kit, 3, 4, sometimes 5 filters in one box. But every filter you add changes your back focus, your reflections, your star shapes, your workflow. Instead of learning one variable, you suddenly have 6. That's not an upgrade. That's complexity you don't need in your first year. So the rule is simple: pick one hero. If you're using a color camera, choose a good dual band filter and learn how it behaves. One filter means one workflow, one set of calibration frames, one predictable night under the sky. And until you truly understand how that single piece of glass affects your data, adding more only slows you down. And while we're talking about filters, here's a secret most beginners aren't told. Every piece of glass you insert shifts your back focus. A typical 2mm filter will move your focus point by about 0.6 millimeters. That tiny shift can distort star shapes and ruin your corners without you ever realizing why. Before you buy anything expensive, buy digital calipers. Learn your spacing. Fix your optical train. That alone will transform your results. Next comes the trap everyone falls into, thinking narrowband filters shorten exposure times. In reality, they do the opposite. A narrow filter blocks almost all incoming light. It cleans the signal, but it also starves the sensor. To get a smooth, clean image, you need hours, many hours of integration time. 1 hour is not an image. It is a preview. At the beginning, 5 hours should be your minimum goal on a target. Not because the filter is weak, but because the physics demands it. And yes, you'll see people using 3 nanometers filters and producing extraordinary images. But ultra-narrow filters are not beginner tools. They starve your guide camera, dim your stars, and magnify every weakness in your mount and tracking. They only shine when everything else in your system is already near perfect. Start with 6 or 7 nanometers. They are bright, forgiving, and far easier to master. Then there's the 2 AM mistake, dew. Filters attract moisture and fingerprints like magnets. One tiny patch of condensation can distort a whole night of exposures. Before you buy your second filter, buy a dew strap. And always check orientation. Most filters have a reflective side that must face the telescope. Get it backward, and you'll introduce reflections that look like UFOs floating through your data. When you put all of this together, the message is simple. Keep your system clean and minimal. Don't complicate your setup before you understand the fundamentals. Pick one filter, learn it completely, build confidence, and grow from there. In astrophotography, the sky rewards patience far more than equipment. You don't need a drawer full of filters. You need time under the stars, a consistent workflow, and the patience to master one variable at a time. The night sky isn't going anywhere. Take your time, learn the craft, and your images will grow with you. With that, happy star hunting from Edisla. If you've made it this far, drop your thoughts. We learn and grow from your input.